Hey friend, welcome. Tonight, let's drift through the quiet science of the universe, where every sound, every thought, and every heartbeat slows with the stars. So find your calm, let the cosmos keep you company, and fall asleep to wonder. Let's begin. Chapter 1. What is energy? The universal constant beneath change. Energy is one of those words we use so often that it begins to feel ordinary, yet in physics it points to something far deeper than everyday meaning. It is not a substance that can be bottled or a mysterious glow that fills machines. It is a property, the measurable capacity of systems to cause change. When something moves, warms, glows, or even exists in a certain position, energy is the hidden quantity that makes those changes possible and keeps the universe consistent. Physicists discovered that energy is conserved. That means in every closed system tested, from mechanical motion to heat, light, and nuclear processes, the total energy remains constant, even though it constantly shifts its form. This is the essence of the first law of thermodynamics, the principle that nothing in the universe is ever truly lost or gained, only rearranged. Across the long history of science, no experiment has ever contradicted it. The difficulty is that energy wears many faces. When an object moves, we call it kinetic energy. When it is poised to move because of its position, we call it potential energy. When atoms vibrate chaotically, we call that thermal energy. When light travels through space, we call it radiant energy. When chemical bonds rearrange, we call it chemical energy. Yet behind all these appearances lies a single conserved quantity. Energy is the universal currency of change, traded endlessly, but never created anew. Consider a simple example. A stone held above the ground possesses energy because of its position in Earth's gravitational field. Let it fall, and that potential energy becomes motion, kinetic energy. When it hits the ground, the movement converts into sound, deformation, and heat. Nothing was lost. It merely changed its form. The same process unfolds on cosmic scales. A collapsing cloud of gas converts gravitational energy into heat and light, igniting a star. The universe itself is a continuous exchange, a great circulation of transformations. The recognition of this unity took centuries to build. In the 19th century, scientists such as James Prescott Joule demonstrated that heat and work are two ways of transferring the same thing, energy. When he stirred water with paddles driven by falling weights, he showed that mechanical motion could be measured precisely as a rise in temperature. The experiment proved that energy was not a material fluid called caloric, as once believed, but a measurable, conserved property linking motion and heat. Richard Feynman later summarized it elegantly. There is a quantity called energy that does not change amid all the changes of the universe. He called it a most abstract idea, but one that works with absolute reliability. Wherever we look, whether in the vibration of atoms or the orbits of planets, the total energy always balances. Modern physics expanded this concept even further. The greatest leap came from Einstein's realization that mass and energy are equivalent. Matter is not separate from energy. It is energy, bound tightly in another form. A small amount of mass contains an enormous amount of energy, which is why nuclear reactions, whether in stars or reactors, release so much power. When nuclei fuse in the core of the sun, a tiny fraction of their mass is converted into radiant energy, the light that warms every living thing on Earth. In this sense, we are literally sustained by the transformation of matter into energy occurring in a star 150 million kilometers away. At the smallest scales, quantum mechanics reshapes our view once again. In the quantum world, energy is not continuous, but comes in discrete packets called quanta. Atoms can only occupy specific energy levels, and when electrons jump between them, they absorb or emit light with precise energies. This quantization explains why each element has its own spectral fingerprint, a pattern of colors unique to its structure. Even when no motion seems to exist, there remains a minimum, restless energy called zero-point energy, a consequence of the uncertainty principle that forbids absolute stillness. The idea grows stranger when we consider empty space itself. Classical physics imagined a perfect vacuum as pure nothingness, but quantum field theory reveals that even the vacuum seethes with activity. Virtual particles flicker in and out of existence, and measurable effects, such as the Casimir force between closely spaced plates, arise from this invisible sea. On a cosmic scale, this underlying energy may be connected to dark energy, the mysterious phenomenon driving the accelerated expansion of the universe. In every sense, nothing is never truly nothing. Energy also defines direction in time. The second law of thermodynamics tells us that while the total energy of a closed system remains constant, the usable energy gradually spreads out. Heat flows from hot to cold, ordered motion disperses into randomness, and entropy, the measure of disorder, increases. This tendency gives the universe its arrow of time. Stars burn fuel, gradients flatten, and energy becomes evenly distributed, yet never disappears. The cosmos is a great engine running steadily toward equilibrium. Within that flow, life represents a remarkable exception. Living systems maintain order by channeling energy through themselves. Plants capture sunlight and turn it into chemical energy through photosynthesis. Animals consume that stored energy, using it to move, think, and build. The energy we eat or breathe eventually dissipates as heat, but while it passes through us, it powers the intricate choreography of biology. Life is not a violation of the laws of energy. It is a local pocket of order sustained by the constant flow from high to low, from star to planet to organism. When physicists define energy precisely, they often turn to symmetry. In modern theory, the conservation of energy follows from the fact that the laws of physics do not change over time. If the universe behaves the same today as it did yesterday, then there must exist a quantity, energy, that remains constant. This profound link between time symmetry and energy conservation, formalized by Emmy Noether, reveals that energy is not merely an accounting trick, but a reflection of the uniformity of nature itself. Despite its elegance, energy is easily misunderstood. People often speak of losing energy or creating energy, but what really changes is its form or quality. A battery discharges not because energy disappears, but because high-grade electrical potential has been converted into lower-grade heat. A car burns fuel not to create energy, but to convert chemical energy into motion. Even in death, the energy bound within living tissue returns to the environment through decay, heat, and new growth. Energy's transformations never end, only the arrangements differ. Every field of science relies on this principle. Engineers design engines by tracking energy efficiency. Chemists predict reactions through energy balances. Astrophysicists study the life cycle of stars by calculating energy output and collapse. Climate scientists trace the flow of solar energy through oceans and atmosphere. The same equation underlies every one of these stories, an invisible thread linking human technology, planetary systems, and the evolution of the cosmos. Energy also sets firm limits on what is possible. No device can produce work without input. No machine can exceed 100% efficiency, and no free energy invention can bypass thermodynamic laws. These restrictions are not failures of imagination. They are reflections of a universe that plays by consistent rules. The same constraints that prevent perpetual motion also make existence predictable, allowing structure, stability, and life itself to emerge. Yet beyond the equations, energy carries a quiet poetry. It is the reason a falling raindrop releases warmth into the air, the reason a violin string hums, the reason your heartbeat converts chemical energy into motion. It is the unseen continuity that links the birth of stars to the firing of neurons, the slow decay of mountains to the flicker of lightning. Energy is the signature of all transformation, the one quantity that remains when the details fade. To understand energy is to see the universe as a web of exchanges, where nothing stands alone. It is the common language of physics, chemistry, biology, and cosmology, the measure that unites motion, matter, light, and life. When we trace its paths, we discover that the same rules guiding galaxies guide our own breath. We are temporary arrangements of energy, intricate patterns of moving atoms held in balance by forces that stretch across the cosmos. As this thought settles, let it bring calm. You are not separate from the universe's flow. You are a momentary harmony within it. The warmth in your skin, the quiet rhythm of your pulse, the fading light of the day, all are energy changing form. Nothing essential is ever lost. When you exhale, you join the endless circulation that has moved through stars, oceans, and countless lives before you. Let that thought ease you. The universe keeps perfect balance, and tonight you are part of that balance. Rest in it. Chapter 2. The first law. Energy cannot be created or destroyed. Among all the laws of physics, few are as quietly profound as the first law of thermodynamics. The statement that energy cannot be created or destroyed. It can only change its form. Behind that simple phrase lies one of the deepest symmetries of the universe, a rule that underpins everything from the beating of a human heart to the shining of a distant star. It is the foundation upon which all other physical processes rest, a quiet assurance that no matter how turbulent change may appear, something essential always remains the same. To grasp what this law truly means, it helps to begin with the idea of a system. Physicists divide reality into systems and surroundings: a star, a cell, an engine, or the entire universe. The first law states that for any closed system, the total energy within its boundaries remains constant. Energy may enter or leave as heat or work, but it never appears from nowhere and never vanishes into nothing. The law does not tell us how energy moves or what form it takes. It tells us that when we finish counting, the ledger must always balance. This idea first emerged from experiments in the 19th century, when scientists sought to understand the nature of heat. At the time, many believed in a substance called caloric, imagined as a weightless fluid that flowed from hot to cold. It took the careful experiments of researchers like James Prescott Joule to show that heat was not a substance but a manifestation of motion. In one of his famous experiments, he allowed a falling weight to turn paddles in a container of water, measuring the rise in temperature. The result demonstrated that mechanical work and heat were interchangeable. A precise quantity of mechanical energy always produced an equivalent quantity of heat energy. That discovery shattered the caloric theory and confirmed the first law's central claim: Energy is conserved, whatever its form. This realization unified many separate fields of science. The same rule that governed spinning wheels also governed burning fuel, flowing electricity, and glowing stars. Whether one studies chemistry, mechanics, or radiation, energy never disappears. Every process in the universe is a conversion, a translation from one language of energy to another. The steam engine, the electric circuit, and the photosynthetic leaf are all manifestations of the same principle. The first law became a bridge connecting every domain of physical science. At its core, the law also encodes a deeper symmetry of the universe. Emmy Noether, one of the most brilliant mathematicians of the 20th century, demonstrated that every conservation law in physics arises from a corresponding symmetry. Energy conservation, she showed, is a direct consequence of the uniformity of time. Because the laws of nature do not change from one moment to the next, energy cannot spontaneously appear or disappear. If the universe were to alter its rules even slightly over time, conservation of energy would no longer hold. The first law is thus not merely an empirical observation. It is an expression of temporal consistency woven into the fabric of reality itself. Understanding this connection allows us to see energy as more than a static quantity. It is the accounting system of change, the invariant that keeps the universe coherent. When you lift a book onto a shelf, you convert chemical energy in your muscles into gravitational potential energy. That energy becomes motion and eventually dissipates as sound and heat. The total energy before and after remains identical, though distributed differently. Even the small fraction of energy that leaves as heat does not vanish. It radiates into the surrounding air, then out into space, joining the universal balance that has persisted since the birth of time. In astrophysics, this same rule governs processes on unimaginable scales. Stars, for instance, convert nuclear potential energy into radiation. In the sun's core, hydrogen nuclei fuse to form helium, and a tiny portion of mass transforms into energy according to Einstein's relation between mass and energy. That energy travels outward as photons, eventually reaching Earth as sunlight. The first law ensures that the energy emitted equals the energy released in the fusion reactions, minus the energy still trapped within the star's structure. Even as a star ages, expands, and dies, the total energy of its matter and radiation remains conserved. Nothing is lost to the void. It only changes its form. On our planet, the law reveals itself in every interaction. Plants absorb sunlight and store part of its energy in the bonds of sugars. Animals consume those molecules, breaking the bonds to release the stored energy for motion and thought. Even when energy becomes unusable, as when waste heat radiates into the atmosphere, it has not vanished. It has simply become more evenly spread out, less able to do work. The first law holds equally for life and for machines, for the burning of stars, and for the blinking of neurons. There is also a subtle philosophical power in the law's simplicity. It tells us that creation and destruction, as we commonly perceive them, are illusions of form. When a candle burns, we might imagine that the wax disappears, transformed into light and smoke. Yet every joule of heat and every photon released correspond exactly to the chemical energy that once resided in the wax. The atoms remain, their bonds rearranged. Nothing is lost. The first law whispers that existence itself is not about appearance or disappearance, but about continual transformation under strict conservation. In practical science, the law acts as a test of truth. Engineers rely on it to check that energy flows in a power plant add up correctly. Chemists use it to calculate the heat of reactions. Meteorologists use it to track energy transfer between ocean and atmosphere. Whenever the totals seem not to balance, it signals that something is missing, perhaps friction, radiation, or an unmeasured chemical change. The law has never failed when the accounting is complete. Its universality is so dependable that scientists treat violations not as evidence against it, but as clues that our description of the system is incomplete. Even in cosmology, where questions of beginnings and endings stretch human imagination, the first law still applies, though in subtler ways. Some cosmological models suggest that the total energy of the universe might be exactly zero, the positive energy of matter balanced perfectly by the negative energy of gravity. If true, it would mean that the cosmos could emerge from quantum fluctuations without violating conservation, because the total sum of energy always remains zero. This idea, discussed by many physicists in the context of cosmic inflation and quantum cosmology, illustrates the extraordinary reach of the first law. It binds not only atoms and stars, but the entire universe in one continuous equation of balance. At the smallest scales, quantum mechanics slightly complicates the picture, but never abandons it. In quantum theory, energy conservation holds on average, though brief fluctuations can occur due to the uncertainty principle. These temporary borrowings of energy, lasting for unimaginably short times, give rise to phenomena like virtual particles. Yet the balance remains. The fluctuations always cancel out when viewed across larger timescales. The law's endurance across both classical and quantum domains is one of the reasons it stands as a pillar of physics. The first law also places limits on human technology. No process can yield more energy than it consumes. Perpetual motion machines, a dream pursued by inventors for centuries, are impossible because they would create energy from nothing. Every working engine, no matter how efficient, must obey the same rule. What goes in must come out, transformed but not multiplied. This limit is not merely a practical obstacle, but a profound expression of nature's consistency. It ensures that the universe does not permit miracles of energy creation, but also that nothing real ever fades entirely away. Yet within these boundaries, the law allows endless creativity. Humans have learned to channel energy with increasing subtlety, from windmills to fusion reactors, from chemical batteries to solar panels. Each of these technologies is a negotiation with the first law, a way of converting energy from one form to another with minimal loss. The same balance that governs the stars also governs our machines. When a spacecraft accelerates, when a computer runs, when a neuron fires, the same cosmic accounting unfolds. There is, perhaps, something profoundly reassuring in that permanence. In a universe of flux and impermanence, energy is the measure that endures. It cannot be summoned from the void, nor can it fall into oblivion. It simply migrates, eternally reshaping itself into new patterns. From the slow drift of galaxies to the spark of a thought, every process is a line in the same cosmic ledger. The first law tells us that even when forms dissolve, the essence persists. For all its elegance, the law is not obvious to human intuition. We live in a world where things begin and end, where fires burn out and lives fade. It takes the discipline of science to reveal that beneath those endings lies continuity. When a star exhausts its fuel, it collapses or explodes, spreading its material and energy into space. From that debris, new stars and planets form, continuing the cycle. The energy of one generation of stars becomes the light of the next, and eventually the warmth of life itself. On human scales, the same is true. The energy that animates a body today will someday flow back into the environment, into air, soil, and light. This realization is more than scientific. It is existential. It means that the universe wastes nothing. Every breath you take carries the recycled energy of ancient stars. The warmth of your body, the motion of your thoughts, the pulse of electricity in your brain, all of it is borrowed from a universal reservoir that has existed since the beginning of time. The first law assures you that nothing essential ever disappears. What seems to die only changes form. What seems to end continues in another guise. So, as you let your thoughts slow, imagine the quiet constancy that underlies the motion of the world. Energy flows through you just as it flows through the oceans and the stars. It has no beginning and no end. You are part of that circulation, a brief, beautiful organization of universal energy. When you rest, that flow continues, gently, endlessly, carrying the memory of your warmth into the vast balance of the cosmos. And somewhere, in the dark stillness between stars, the same law holds steady, keeping perfect account of every transformation. Chapter 3. The Many Faces of Energy, Motion, Position, and Transformation. If the first law of thermodynamics teaches us that energy is conserved, this chapter reveals its endless versatility. Energy never stands still. It appears in countless forms, hides within matter, vibrates through fields, and drives every process of transformation in the universe. Though its total quantity is fixed, its expression is infinitely varied. Understanding these forms is to understand the choreography of nature. The way movement, position, and transformation are woven together in one seamless fabric of exchange. When we say that an object in motion possesses energy, we are speaking of kinetic energy, the energy of movement. It is perhaps the most intuitive of all forms, the direct measure of how much work an object can perform by virtue of its velocity. The faster something moves, the greater its capacity to impart change to other things. A rushing river, a spinning planet, or a flying particle all carry kinetic energy. Yet even here, energy is not merely motion itself. It is the potential of motion to cause change. It links directly to momentum and to the mass of the moving body, both of which ground our sense of inertia and impact. From the swirling of air currents to the graceful arc of a comet, kinetic energy defines the universe in motion. Equally important, though less visible, is potential energy, the energy of position or configuration. A stone perched on a cliff holds energy because gravity can act upon it. A compressed spring, a stretched rubber band, or an electric charge held apart from another, each embodies stored potential, ready to release when the constraints are lifted. This kind of energy is deeply relational. It depends not on an isolated object, but on how that object is situated within a field of forces. It represents the tension between what is and what could be. In that sense, potential energy underlies the very concept of transformation. It is the pause before motion, the poised balance that gives rise to change. Thermal energy introduces another layer of complexity. On the scale of everyday experience, heat seems distinct from motion, but at the microscopic level it is motion, the random agitation of atoms and molecules. As temperature rises, these particles vibrate more intensely, colliding and transferring energy among themselves. When we feel warmth, we are sensing the collective motion of trillions of invisible constituents. This microscopic motion manifests as macroscopic phenomena. the expansion of gases, the conduction of heat through solids, the convection of air and water. In thermodynamics, thermal energy acts as the great equalizer, flowing naturally from regions of higher temperature to lower, in accordance with the second law. It is the gentle smoothing of differences, the diffusion of motion until balance is restored. Chemical energy lies hidden in the bonds that link atoms together. Those bonds are not static. They represent subtle balances of electromagnetic forces. When bonds form or break, the distribution of electrons changes, and energy is either absorbed or released. Combustion, metabolism, and photosynthesis are all processes of chemical transformation, controlled rearrangements of atoms that shuffle energy among molecular structures. The burning of fuel releases energy that was once captured from sunlight by ancient photosynthetic organisms. Every cell in your body relies on this same chain of transfers, using energy stored in molecules like adenosine triphosphate to drive the complex reactions of life. Chemistry, in this view, is the story of how energy hides in structure and reveals itself in transformation. On a larger scale, gravitational energy sculpts the cosmos. Gravity is the architect of stars, planets, and galaxies. When matter falls inward under its own attraction, potential energy converts into kinetic and thermal energy, igniting nuclear fusion in stellar cores. Every sunrise is powered by this cycle of gravitational collapse and radiative release. Even black holes, the most extreme gravitational objects, participate in the same conservation, though their mechanisms remain partially veiled by theory. In the grand economy of the cosmos, gravity is the collector, gathering matter and compressing energy into new forms. Electromagnetic energy, meanwhile, governs nearly all phenomena of daily life. Light, radio waves, and X-rays are all oscillations of electromagnetic fields. Electric currents power our cities. Magnetic fields guide compasses and shape cosmic plasma. The interplay between electricity and magnetism, unified by Maxwell's equations, reveals that they are different aspects of a single phenomenon. A moving electric charge generates a magnetic field, and a changing magnetic field induces an electric current. This continual interplay transfers energy through empty space as electromagnetic radiation, the light that reaches us from stars and galaxies, carrying the story of their distant past. Nuclear energy represents one of the most concentrated forms known to physics. Within atomic nuclei, protons and neutrons are bound together by the strong nuclear force, a fundamental interaction far more powerful than electromagnetism at short distances. When nuclei split in fission or combine, in fusion, small changes in binding energy release enormous amounts of power. This is the process that fuels stars and, in controlled form, nuclear reactors on Earth. The transformation of mass into energy in these reactions illustrates the deep unity between matter and energy described by Einstein's theory of relativity. It is a reminder that every atom carries within it the potential for transformation on cosmic scales. Each of these forms, kinetic, potential, thermal, chemical, gravitational, electromagnetic, and nuclear, are facets of one principle: energy's ability to transform. The boundaries we draw between them are conveniences for thought and measurement, not divisions in nature. When a thunderstorm forms, gravitational potential drives motion in the atmosphere. Friction turns that motion into heat, and electric charges build up to release energy as lightning. The process is continuous, an unbroken exchange across forms. Likewise, in a living organism, chemical energy becomes mechanical work, then heat, then radiant energy dissipated to the environment. Energy is a universal language that everything speaks, each translation adding a new accent, but not altering the underlying meaning. The transformations of energy define the dynamics of the universe. When energy changes form, it drives processes that shape matter, govern climate, sustain life, and guide evolution. Yet each transformation obeys constraints. Some conversions are easy, mechanical work into heat, while others require specific conditions. For instance, chemical energy cannot spontaneously become organized motion without a mechanism to direct it, such as the molecular machinery within living cells. These constraints arise from the second law of thermodynamics, which dictates the direction of energy flow. It ensures that while energy is conserved, its usefulness tends to degrade. The universe thus evolves not toward loss of energy, but toward equilibrium. A subtle but profound distinction. Scientists often visualize energy flow using the concept of energy pathways. In Earth's system, solar energy drives photosynthesis, winds, and ocean currents. In a star, nuclear energy flows outward as radiation, maintaining balance against gravitational collapse. In a galaxy, gravitational energy becomes heat and light as matter falls into stars. Everywhere, the story is one of redistribution. Energy moves from concentrated to diffuse, from ordered to random, from local structures to cosmic background. Even the faint cosmic microwave background radiation is a remnant of this long history. The cooled echo of a once blazing universe, energy stretched across space by cosmic expansion. What makes energy's transformations so profound is that they knit together phenomena of radically different scales. The same principles that describe a pendulum swinging in a room also describe the orbit of a moon or the spiral of a galaxy. The same conservation that governs a chemical reaction governs the formation of black holes. This unity gives science its predictive power. It allows us to connect events across billions of light years and across the smallest dimensions of atomic interactions, all through the same vocabulary of energy transformation. It also brings a measure of humility. We are creatures made entirely of these exchanges. The warmth in your body right now is the afterglow of ancient nuclear reactions in distant stars. The energy that powers your thoughts once traveled as sunlight, captured by plants, transformed into chemical bonds, and released again through metabolism. Every heartbeat is a conversion, every breath a transaction in the universe's vast economy. To live is to participate in energy's endless transformation, not apart from it, but as a fleeting pattern within it. Energy, in all its forms, is thus both mechanism and metaphor. It explains how stars shine and why we feel warmth, but it also speaks to the deeper continuity of existence. There is no boundary between the energy that lights the galaxies and the energy that fuels a single human cell. The universe, from the smallest vibration to the largest structure, is one continuous act of transformation, forever changing and forever conserved. When we contemplate this, a quiet perspective emerges. Nothing in existence is static. Everything is energy in motion, energy in waiting, energy in transition. The atoms that compose you were once part of stars, and the energy that moves through you will one day return to the cosmos in another form. There is no true stillness, only balance. No real death, only conversion. The same energy that burns in the core of a star hums softly within you. The same laws that move galaxies govern the rhythm of your pulse. As the day draws to a close, you might imagine all the transformations around you. The cooling air, the fading sunlight, the slow turning of Earth beneath the stars, and recognize that you are part of that vast continuum. Energy flows endlessly, reshaping itself through every form it can take, but never disappearing. It has always been here, and in some form it always will be. Let that thought be a calm reminder. In a universe of constant transformation, you too are energy, briefly arranged, beautifully alive, and forever part of the same unbroken flow. Chapter 4. E equals mc squared, How Matter Becomes Energy. At the dawn of the 20th century, a young patent clerk named Albert Einstein quietly redrew the boundaries of reality. Among the insights that emerged from his special theory of relativity, one stood apart for its simplicity and depth: the realization that mass and energy are not distinct. They are two expressions of the same underlying substance, convertible one into the other. What appears solid and unmoving, every atom, every stone, every living being, is in truth a form of condensed energy, bound within itself by the forces of nature. Before Einstein, physicists treated matter and energy as separate realms. Matter was the substance of the universe, energy was its motion and change. The two interacted but were thought to belong to different categories of being. Einstein's revolutionary insight was that they are interchangeable. When he examined how motion and energy behave for observers moving at different speeds, he found that an object's energy increases with velocity, and with it, its inertia. The implication was staggering. Energy contributes to mass. Matter, in turn, can be understood as energy that has been frozen into structure. The connection between mass and energy means that even a small amount of matter holds immense energy within it. Although we cannot use numerical expressions here, the conversion factor involves the square of the speed of light, a vast multiplier that reveals how tightly energy is compacted in matter. A single gram of material, if completely transformed, could in principle release more energy than enormous quantities of chemical fuel. This is not theoretical imagination. It is the mechanism by which the universe shines. In the core of the sun, hydrogen atoms fuse to form helium. The mass of the resulting helium nucleus is slightly less than that of the hydrogen nuclei that formed it. The missing mass has been converted into radiant energy, carried outward by photons that warm and light our world. Over the lifetime of a star, this continuous conversion of mass into energy sustains the cosmic furnace. The sunlight that reaches your face is mass that has become pure energy, a transformation taking place 150 million kilometers away. Without that exchange, there would be no life, no weather, no light. The same principle explains some of the most powerful events in the cosmos. When massive stars collapse, the conversion of mass into energy drives supernovae, explosions so intense that for a brief time they outshine entire galaxies. In these cataclysms, elements heavier than iron are forged, scattering the building blocks of planets and living matter into space. Every atom of carbon, oxygen, heat, and iron within your body was created through such transformations, born from the conversion of matter into energy in stars that lived and died long before our sun existed. On Earth, humanity has learned to harness this principle. Nuclear fission, the splitting of heavy atoms such as uranium, releases energy because the fragments together weigh slightly less than the original nucleus. In nuclear fusion, the same process that powers stars, light nuclei combine, and the lost mass appears as energy. In controlled reactors, this energy can provide electricity for cities. In weapons, it can destroy them. Both are reminders of the immense power that rests within matter and of our responsibility in wielding it. The physical law itself is neutral. It is humanity's choices that determine whether the result is creation or devastation. Mass-energy equivalence also underlies modern particle physics. Experiments in high-energy accelerators have shown that energy can indeed create matter. When particles collide at near-light speed, the kinetic energy of motion is converted into new particles that did not exist before. Conversely, when unstable particles decay, their mass becomes energy, radiating away as light and other forms of radiation. These processes mirror those that occurred in the first moments of the universe, when energy condensed into matter as the cosmos cooled. Each experiment is, in essence, a miniature echo of cosmic creation. In this framework, mass itself is no longer viewed as an intrinsic property of matter, but as a manifestation of energy bound within fields. Modern theories describe particles not as tiny solid objects, but as excitations in underlying quantum fields. The strong nuclear force, which binds quarks inside protons and neutrons, accounts for most of the visible mass in the universe. Even the electrons and quarks themselves gain mass through their interaction with the Higgs field, an invisible energy field that permeates space. Matter, then, is a pattern of energy stabilized by fundamental interactions. What feels solid beneath our hands is, in truth, a symphony of confined energy. The implications of this unification reach into cosmology. In the early universe, matter and energy were indistinguishable within a hot, dense plasma. As expansion and cooling proceeded, some of that energy congealed into particles of matter and antimatter. Almost all of those pairs annihilated, releasing their energy as radiation. The tiny surplus of matter left behind formed the galaxies, stars, and planets we see today. In this sense, everything that exists, every atom, every photon, every structure, is a descendant of the primordial conversion between energy and matter that began with the Big Bang. This equivalence also shapes gravity itself. In Einstein's later theory of general relativity, both mass and energy curve the geometry of space-time. Gravity is not a force in the classical sense, but the effect of energy telling space how to bend and space telling energy how to move. Light follows the same curved paths as matter because it carries energy and momentum even without mass. The connection between mass and energy is therefore woven into the structure of space-time, governing the motion of planets, the dynamics of galaxies, and the evolution of the universe itself. In everyday life, the principle remains hidden but omnipresent. The energy produced when we burn fuel, digest food, or even think arises from minute shifts in the binding energies of atoms and molecules, far too small to detect as changes in mass, but real nonetheless. Every chemical reaction, every ray of sunlight, and every heartbeat reflects the same law in miniature. Energy flows from one form to another, and with each exchange, a corresponding amount of mass is subtly rearranged. Seen through this lens, matter is not the opposite of energy, but its quiet expression. The universe has chosen to store some of its energy in the form of substance, slow-moving, enduring, capable of structure. From that structure, complexity arises. Stars form, planets coalesce, life evolves, and eventually consciousness appears to contemplate the process itself. When Einstein revealed the unity of mass and energy, he did more than explain physical phenomena. He showed that everything that exists shares a single origin. There is no dividing line between the material and the immaterial, between the light of the stars and the atoms of our bodies. This realization carries an existential stillness. the energy that fuels your heartbeat once burned in distant suns. The particles that form your body were created in ancient explosions that illuminated the early galaxy. When you move, think, or speak, the energy within you flows outward, joining the great exchange that connects every part of the cosmos. One day, the matter that composes you will dissolve back into the world, and its energy will take new forms. Heat in the atmosphere, light from another star, perhaps even the motion of a future life. Nothing will be lost, it will only change. Einstein's equation is often recited as a symbol of power, but its true meaning is harmony. It tells us that the universe is whole, that the solidity of matter and the brilliance of light are different expressions of the same eternal rhythm. Every sunrise, every breath, every flicker of consciousness is part of that rhythm, matter transforming into energy and energy into matter in an unending dance. The cosmos wastes nothing, it only transforms. And so, as the day fades, you might let this thought rest within you. You are starlight made slow, energy held gently in a pattern long enough to dream. The same principle that illuminates galaxies sustains the warmth of your body. When you exhale, when you sleep, when you finally return to stillness, that energy continues, unchanged, unbroken, flowing back into the universe that first gave it shape. Chapter 5. The Quantum Landscape. Energy in the Smallest Scales. If the first chapters revealed how energy governs the visible universe, powering stars, sustaining life, and shaping matter, this one dives beneath the surface into a realm where the ordinary rules begin to blur. Here, at the smallest scales of existence, energy no longer behaves like a smooth, continuous quantity. It arrives in discrete packets, fluctuates unpredictably, and connects phenomena across distances in ways that defy common sense. This is the quantum landscape, a world where energy becomes both grainy and ghostly, and where the universe's deepest mysteries reveal themselves. At the start of the 20th century, physicists faced a crisis. Classical theories could not explain the behavior of light and heat at the atomic level. Experiments showed that matter emitted and absorbed energy in sharply defined amounts rather than in a continuous flow. Max Planck, in an act of mathematical desperation, proposed that energy comes in indivisible units he called quanta. He introduced a constant of nature, now known as Planck's constant, to describe the scale of these packets. What began as a temporary fix became the foundation of quantum physics. It meant that energy itself has a smallest possible increment, a kind of atomic structure of action. Soon after, Albert Einstein extended this idea to light. He suggested that light, which had long been understood as a wave, also behaves like a stream of particles, photons, each carrying a discrete quantum of energy. That radical thought explained the photoelectric effect, where light striking a metal surface can eject electrons only if its frequency is above a certain threshold. The energy of the photons, not their brightness, determined the outcome. For this insight, Einstein received his Nobel Prize, and the concept of quantized energy became permanent in physics. The old, smooth picture of nature was replaced by a universe built from discrete exchanges. In atoms, these energy quanta determine everything. Electrons can occupy only specific orbits or energy levels around a nucleus. When an electron moves from a higher level to a lower one, it emits a photon whose energy matches the gap between those levels. When it absorbs a photon, it leaps to a higher orbit. This is why each element has its own characteristic spectrum. a set of bright lines or colors that act as a fingerprint of its atomic structure. Spectroscopy, the study of those patterns, allows scientists to identify the composition of distant stars and galaxies, reading their light as a cosmic code written in energy transitions. At this scale, energy and matter intertwine in ways that challenge classical intuition. Particles behave both as localized points and as spread-out waves. Their energies are not sharply defined until measured. Instead, they exist as probabilities across possible states. The equations of quantum mechanics, first formulated by Schrödinger and others, describe how these probabilities evolve. When a measurement occurs, the probabilities collapse into a definite outcome, and energy assumes a precise value. This probabilistic nature is not a flaw of our instruments, but an intrinsic feature of reality. Even with perfect knowledge, the future behavior of a quantum system can only be described statistically. Energy in the quantum realm also resists perfect stillness. According to the uncertainty principle introduced by Werner Heisenberg, the more precisely we know a particle's position, the less precisely we can know its momentum and therefore its energy. This means that even at absolute zero temperature, where motion should theoretically cease, particles retain a small, unavoidable agitation. This irreducible motion gives rise to what physicists call zero-point energy. The universe cannot be completely quiet. Every atom, every field, every point in space hums faintly with invisible energy, even in what we call the vacuum. These fluctuations have measurable consequences. In a famous phenomenon known as the Casimir effect, two uncharged metal plates placed extremely close together in a vacuum experience a subtle attraction. The reason lies in the quantum fields that fill space. The presence of the plates restricts the wavelengths of the virtual particles that can exist between them, creating a slight imbalance in the surrounding vacuum energy. The result is a measurable force that can only be explained through quantum theory. Experiments have confirmed this effect repeatedly, providing tangible evidence that even empty space contains restless energy. Quantum mechanics also reveals that energy can be borrowed, but only briefly. The uncertainty principle allows fluctuations in energy to occur for extremely short times, producing transient pairs of particles and antiparticles that appear and disappear. These virtual particles influence the behavior of real particles, altering their properties in subtle but measurable ways. In quantum electrodynamics, this seething activity of the vacuum contributes to the fine details of atomic spectra and the magnetic moment of the electron. The precision with which these predictions match experiments to better than 1 part in a trillion is one of the great triumphs of modern physics. At the same time, quantum physics blurs the line between energy and information. The energy levels of atoms encode how they interact, while entanglement, the mysterious linkage between particles separated by distance, allows energy and correlations to be shared across space in ways that defy classical separation. When two particles are entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Experiments have confirmed this repeatedly, ruling out any hidden mechanism that transmits signals faster than light. What this means for energy conservation is subtle but consistent. The total energy of the combined system remains conserved, but its distribution is no longer confined to local space. Energy and information weave together in a non-local tapestry. In the quantum world, fields rather than particles are the ultimate carriers of energy. Each type of particle corresponds to a field that permeates space, and particles are excitations, tiny ripples within those fields. Photons are vibrations of the electromagnetic field. Electrons are excitations of the electron field. Quarks are ripples in the quark fields. Even the Higgs field, whose excitation was confirmed at CERN, is a background sea of energy that grants mass to other particles. Thus, the concept of energy extends beyond motion and potential. It becomes the very texture of reality. Everything that exists is an arrangement of energy vibrating within these universal fields. Quantum mechanics also connects with thermodynamics in unexpected ways. On the microscopic level, energy exchanges are not deterministic, but probabilistic, leading to the emerging field of quantum thermodynamics. This discipline explores how heat, work, and entropy behave when systems contain only a handful of particles. It shows that the familiar macroscopic laws like the conservation of energy and the second law of thermodynamics arise naturally from the average behavior of countless quantum interactions. Even randomness has structure, and through it, the order we see in the larger world emerges from the quantum fluctuations beneath. One of the most profound implications of quantum physics is that energy can manifest from what appears to be nothing, but only within the boundaries of the laws that govern it. In the early universe, quantum fluctuations may have seeded the irregularities that later grew into galaxies and clusters of matter. The energy of these fluctuations, amplified during cosmic inflation, could have sculpted the large-scale structure of the cosmos. Thus, the tiniest events in the quantum vacuum may have left imprints visible across billions of light years. The small becomes the architect of the vast. Quantum theory also reveals the limits of our knowledge. Because energy at the smallest scales is inherently uncertain, no measurement can provide perfect precision. Nature keeps some information hidden, as if reminding us that observation is not separate from participation. The energy we measure depends on how we choose to look, and the act of measurement changes the system we observe. In that sense, energy in the quantum world is not a passive quantity to be tallied, but a relationship, a dynamic interplay between observer and observed. Despite its strangeness, the quantum description of energy has proven astonishingly accurate. Quantum mechanics underpins the technologies of modern civilization. Semiconductors, lasers, magnetic resonance imaging, and quantum computers all rely on its principles. The screens we read, the lights that illuminate our nights, the electronics that carry our voices, all are products of understanding how energy behaves when confined to the microscopic scale. The everyday world is built upon the quiet rules of the quantum. Yet beyond technology, there is wonder. The quantum landscape reveals a universe that is alive with motion, even in its stillness, structured yet unpredictable, limited yet infinite in possibility. It shows that energy, far from being a static quantity, is a ceaseless conversation between probability and actuality. The boundaries of existence flicker with activity. What seems empty teems with creation and annihilation. The vacuum itself is a restless ocean, and every atom, every photon, every breath is a wave upon its surface. In contemplating this, one begins to sense a strange comfort. The same quantum energy that sustains stars also hums invisibly through your body. The warmth in your skin and the glow of starlight obey the same microscopic laws. You are built from vibrations of fields that have existed since the beginning of time, and when your form dissolves, those vibrations will continue in other patterns. Energy will not end, it will merely shift its rhythm. The quantum realm reminds us that certainty is an illusion. Beneath the solid surfaces of matter, existence dances, a blur of probabilities, an endless exchange of invisible energy. The stillness we perceive is woven from fluctuations too fast for our senses to grasp. And yet, from that restless foundation, the universe creates form, order, and life. It builds mountains and minds from the same trembling void. So as you settle into quiet, imagine the space around you not as empty but alive, filled with invisible waves of energy, with particles appearing and vanishing in silence. You are part of that sea, a pattern of quantum energy briefly self-aware. Every thought, every heartbeat, every breath is an echo of the universe's first fluctuations. When you rest, that energy continues unchanged, flowing through the infinite fabric of existence. The smallest scales hold the greatest truth, that nothing is truly still and nothing is ever lost. Chapter 6. The energy of the vacuum. Nothing is never nothing. When we imagine emptiness, we picture a vast, silent void, an expanse stripped of matter, motion, and light. In everyday language, the word nothing suggests an absence so complete that it cannot contain anything at all. Yet in modern physics, this image collapses. The more precisely we study the vacuum, the more we find that emptiness is an illusion. Space is not empty. It seethes with energy, structure, and activity, even when every particle has been removed. What we call nothing is, in truth, the foundation of everything. The transformation of this idea began in the early 20th century with the birth of quantum mechanics and quantum field theory. Classical physics viewed the vacuum as a simple background, a stage upon which matter and radiation acted, but which itself remained unchanged. Quantum theory replaced this notion with one far stranger and more dynamic. It revealed that fields, not particles, are the fundamental components of reality, and that these fields exist everywhere, even in the absence of matter. The vacuum, in this sense, is not the absence of fields, but their lowest energy configuration. And as it turns out, even that lowest state is restless. Because of the uncertainty principle, no field can ever be perfectly still. If a field were to have exactly zero energy, its state would be precisely defined, violating the rule that energy and time cannot both be known with infinite accuracy. As a result, every field fluctuates slightly, producing a faint, irreducible energy that permeates all of space. This is the so-called zero-point energy, the minimal vibration that remains even at absolute zero temperature. The vacuum is not quiet. It hums faintly with these omnipresent fluctuations. Evidence of this invisible energy comes from experiments and observations that would otherwise be impossible to explain. One of the most striking examples is the Casimir effect, in which two parallel metal plates placed extremely close together in a vacuum experience a gentle force pulling them toward each other. The space between the plates allows fewer modes of electromagnetic fluctuation than the space outside, creating a tiny difference in pressure. Though subtle, this force has been measured repeatedly with high precision, confirming that quantum fluctuations of the vacuum are real and measurable. On atomic scales, vacuum fluctuations also alter the properties of particles. The electron, for instance, is constantly surrounded by a cloud of virtual particles, brief flashes of existence arising from the vacuum's energy. These virtual particles slightly modify the electron's charge and magnetic moment, effects predicted by quantum electrodynamics and confirmed by experiments to astonishing precision. The match between theoretical predictions and observations, accurate to better than 1 part in a trillion, stands as one of the great successes of modern science. It is proof that even empty space is an active participant in the workings of nature. When we look beyond atoms to the cosmos, the implications become even more profound. In Einstein's theory of general relativity, the energy and pressure of any form of matter or radiation determined how spacetime curves. This includes the energy of the vacuum itself. If the vacuum has energy, it must influence the geometry of the universe. For decades, physicists assumed that the average energy of empty space was exactly zero because any non-zero value would have observable gravitational consequences. Yet the discovery of cosmic acceleration in the late 20th century changed that picture completely. Observations of distant supernovae and the cosmic microwave background revealed that the expansion of the universe is speeding up, driven by a mysterious component that behaves like a uniform energy filling all of space. This phenomenon is now called dark energy. The simplest explanation for dark energy is that it is vacuum energy, the same zero-point energy that arises from quantum fields, but acting on a cosmic scale. In this view, every cubic centimeter of space contains a tiny amount of energy that exerts a gentle but persistent pressure, pushing galaxies apart. However, this simple idea leads to one of the deepest puzzles in physics. Calculations of the vacuum energy predicted by quantum field theory produce an enormous value, vastly greater than what is observed. The discrepancy between theory and observation is so large that physicists have called it the worst theoretical prediction in the history of physics. Reconciling this difference remains one of the central challenges of modern cosmology. Some scientists suspect that the answer may lie in an unknown symmetry or mechanism that cancels most of the vacuum energy, leaving only a small residue that drives cosmic acceleration. Others propose that dark energy may not be constant at all, but a dynamic field that evolves over time. Whatever the truth, the mystery forces us to confront an unsettling idea. The fate of the entire universe depends on the energy of what we once thought was nothing. The vacuum, far from being passive, governs the grandest motions of the cosmos. Even within this sea of energy, the vacuum is remarkably stable. If it were to shift to a lower energy state, if some deeper, true vacuum existed, the change would release enormous energy, reshaping the fundamental constants of nature and obliterating all known structures. This speculative scenario, known as vacuum decay, has been discussed seriously by physicists. Calculations based on our current understanding of particle physics suggest that our universe may, in principle, be in a metastable vacuum state, stable for trillions of years, but not absolutely eternal. If such a transition ever occurred, it would spread outward at the speed of light, rewriting the laws of physics as it went. Though there is no evidence that this is imminent, the mere possibility is a reminder of how delicate the universe truly is, suspended between existence and a deeper, unknowable ground state. At the quantum level, the vacuum also shapes how particles interact through a process known as renormalization. Because the vacuum is never truly empty, particles continually exchange energy with it, altering their effective masses and charges. The success of quantum field theory in predicting these effects is one of the triumphs of modern science. Yet it also raises philosophical questions. If every measurable property of matter depends on the vacuum's fluctuations, then in a profound sense, everything that exists is built from nothing. or rather, from the structured energy of the vacuum itself. The material world emerges from what appears to be empty space, like waves rising from a calm sea that is never truly still. Some physicists have extended this idea to its ultimate conclusion, that space, time, and matter might all be emergent phenomena arising from quantum fluctuations. In this view, the vacuum is not merely filled with fields, but is itself a dynamic network of relationships. The geometry of space-time, the existence of particles, even the flow of time may arise from the collective behavior of the quantum vacuum. Though speculative, this picture aligns with efforts in quantum gravity and string theory, which suggest that space is composed of discrete units of information rather than a smooth continuum. The vacuum, then, becomes the fundamental canvas of reality, a reservoir of potential from which everything else arises. On the scale of human life, these concepts may seem abstract and distant, yet their consequences are all around us. The light from every star, the stability of every atom, the evolution of the cosmos, all depend on the energy of the vacuum. Even the passage of time, defined by the expansion of space, is shaped by the vacuum's persistent pressure. What seems like nothing is, in fact, the most universal presence there is. It is tempting to ask whether this omnipresent energy could ever be harnessed. Popular imagination often envisions tapping the vacuum as an infinite energy source, a kind of cosmic battery. But the laws of physics are not so generous. The energy of the vacuum cannot be extracted without changing the entire structure of the fields themselves. It represents the lowest possible state, meaning there is no below from which to draw additional energy. Attempts to engineer devices that claim to extract energy from the vacuum have consistently failed because they would violate fundamental conservation laws. The vacuum's energy is real, but it is not available for use. It defines the baseline of existence, not a resource within it. Still, there is something almost spiritual in recognizing that what we once called nothing is the source of everything. The vacuum is not a void to be feared, but a field of endless potential. Its fluctuations birth the first particles. Its energy drives the universe's expansion. Its structure holds the laws of physics themselves. Every atom in your body, every photon you see, every sound you hear, traces its ancestry back to this invisible ocean of energy. You are a wave that rose briefly from the vacuum and became aware of itself. When you think of nothingness now, let it be a different kind of image. Not an empty space, but a quiet fullness, a background hum of creation. The same vacuum that underlies distant galaxies also surrounds and sustains you. Between every atom in your body lies more vacuum than matter. Yet within that apparent emptiness vibrates the energy that binds the cosmos together. You are woven into that vibration, inseparable from it. There is no true void. Even silence is filled with motion. Even darkness glows faintly with the energy of the unseen. And when you close your eyes at the end of the day, remember that the space around you is not empty but alive. A limitless sea of potential, whispering softly in the language of quantum fluctuations. The universe rests upon that invisible foundation, and so do you. Nothing is never nothing. It is the quiet heartbeat of everything that ever was and everything that will ever be. Chapter 7. Entropy and the Flow of Energy Through Time. In the quiet rhythm of the universe, energy moves. It flows from one form to another, from concentrated to dispersed, from order to disorder. The principle governing that flow is called entropy. and it lies at the heart of the second law of thermodynamics. It is one of the deepest truths known to science, a rule that not only shapes the fate of stars and galaxies, but also underlies the passage of time itself. Through entropy, the cosmos gains its direction. While the first law of thermodynamics assures us that energy is conserved, the second law tells us why change has a direction, why we remember the past but not the future, why heat moves from hot to cold, why time itself seems to flow one way. To grasp entropy, we must first understand it not as a measure of disorder, as it is often simplistically described, but as a measure of how energy is spread out among the possible configurations of a system. In any closed system, there are many microscopic ways its particles can be arranged while still appearing the same on a large scale. Entropy increases when energy becomes more evenly distributed among those possibilities. A hot cup of tea cooling on a table is a small example of this law at work. The thermal energy of the tea spreads into the air, equalizing temperatures, and in doing so, the total entropy of the system increases. No external force drives this process. It is simply the most probable outcome. Nature favors balance. The second law of thermodynamics tells us that in an isolated system, entropy never decreases. That does not mean that local order cannot form. Stars ignite, crystals grow, life evolves. But such order always comes at the expense of increased entropy elsewhere. The universe, viewed as a whole, marches steadily toward greater uniformity. Over cosmic timescales, this flow of energy toward equilibrium defines the arrow of time. It gives the universe its irreversible character. Things happen, energy spreads, and even though the total amount of energy remains constant, its ability to do work gradually diminishes. Entropy is what turns potential into history. Every process that has occurred since the beginning of the universe, from the fusion of atoms and stars to the flicker of thought in the human brain, has taken place within this one-way current. The expanding universe began in a state of remarkably low entropy, an improbable condition of extreme concentration and order. As it evolved, energy flowed outward, structures formed, and entropy increased. Today, the stars that shine and the galaxies that swirl are transient islands of low entropy, powered by the difference between concentrated energy sources and the cold emptiness of space. When that difference eventually vanishes, the stars will go out, and the universe will approach what physicists call heat death, a state of maximum entropy, where energy is uniformly distributed and no further work can be done. This long-term fate is not a prediction of destruction, but of stillness. It represents the end of change, a universe in perfect thermal balance, devoid of gradients to drive motion or structure. The concept of heat death has been discussed since the 19th century, and though it may lie trillions of years in the future, its logic is embedded in the laws of thermodynamics. Yet the same laws that foretell cosmic quiet also make life and complexity possible now. Every living organism, every weather system, every flame exists because energy is flowing from regions of high concentration to low. Entropy is not the enemy of life, but its engine. It defines the gradient that life climbs. In this sense, the second law reveals a paradoxical beauty. The universe's drift toward equilibrium creates the very conditions that allow temporary pockets of order to exist. Earth, for instance, receives concentrated energy from the sun and radiates lower energy infrared light back into space. This flow of energy maintains the temperature difference that fuels weather, drives ocean currents, and sustains biological activity. Life itself is a mechanism for channeling energy while increasing the overall entropy of the universe. Every cell, every organism, every ecosystem takes in low entropy energy and releases high entropy waste, perpetuating the universal trend while briefly defying it locally. From a scientific perspective, entropy also links the microscopic and macroscopic worlds. The statistical interpretation developed by Ludwig Boltzmann showed that the second law arises from probability. In any large system with many particles, the number of disordered arrangements far exceeds the number of ordered ones. Even if order appears spontaneously, it will tend to decay simply because disorder is overwhelmingly more likely. This statistical nature of entropy connects the arrow of time to the sheer mathematics of probability. We move forward in time not because of some metaphysical flow, but because the universe naturally evolves from less probable states to more probable ones. The second law also manifests in information theory, where entropy measures uncertainty or information content. In this framework, developed by Claude Shannon in the mid-20th century, entropy describes the amount of information needed to specify the state of a system. The parallel is striking. Physical entropy quantifies the number of microstates compatible with a given macrostate, while informational entropy measures the unpredictability of a message. This connection hints at something profound, that the flow of energy and the flow of information may be two sides of the same coin. The universe not only evolves energetically, but also computationally, processing information as it unfolds through time. In cosmology, entropy's role is even grander. The early universe began in a state of low entropy, not because matter was highly ordered, but because gravity had not yet sculpted it into stars and galaxies. As gravity pulled matter together, forming dense regions surrounded by vast voids, the overall entropy increased. Black holes, which represent extreme concentrations of mass and curvature, are paradoxically the highest entropy objects known. According to the work of Jacob Bekenstein and Stephen Hawking, a black hole's entropy is proportional to the area of its event horizon, not its volume. When matter or radiation falls into a black hole, its energy and information are not lost but encoded in the horizon's geometry. Even the evaporation of black holes through Hawking radiation obeys the second law. The total entropy of the black hole and its surroundings always increases. The connection between gravity, thermodynamics, and quantum theory remains one of the deepest frontiers of modern physics. Entropy thus binds together every scale of existence. It governs the burning of stars and the decay of atoms, the operation of engines and the aging of living things. In human terms, it even touches memory and consciousness. Our perception of time's flow, of past and future, arises from the accumulation of irreversible processes in the brain. Each thought, each heartbeat, each act of remembering leaves traces of entropy. In a sense, consciousness itself may be the universe's way of witnessing the flow of energy toward equilibrium, a temporary pattern formed by that very flow. This understanding brings both humility and wonder. Entropy is often mistaken for decay, but it is really transformation, the redistribution of possibility. Without it, there would be no sunrise, no evolution, no thought. The universe's drive toward equilibrium gives meaning to motion and time. The stars that illuminate the night sky are the visible evidence of entropy in progress, radiating energy into the cold abyss. Their light eventually fades, but in doing so, they make everything we know possible. The warmth of your body, the breath in your lungs, and the spark of your mind all depend on energy cascading down entropy's slope. The second law also defines the limits of what can be achieved. No process, however ingenious, can convert energy into work without loss. Every engine must shed heat, every computation generates waste energy, every act of life increases the entropy of the surroundings. This is not a failure of design, but the nature of the universe. The laws that make existence possible also set the boundaries within which it must unfold. Perpetual motion in any form is an impossibility not because of mechanical limitations, but because it would require reversing the direction of entropy, turning time backward. As scientific as it is, the concept of entropy carries an unmistakably existential resonance. It suggests that all things move toward dispersion, that order and structure are temporary arrangements in an expanding sea of equilibrium. Yet within that inevitability lies a profound kind of peace. The universe does not resist change, it expresses it. Entropy is not the death of meaning, but its context, the background rhythm against which creation dances. The temporary emergence of complexity, consciousness, and beauty does not violate the second law, it fulfills it. When viewed this way, entropy becomes less a story of decline and more a story of participation. Each of us is a conduit through which energy flows, part of the cosmic process of transformation. The heat we release, the thoughts we think, the lives we live, all are expressions of energy finding new configurations, of entropy quietly increasing. And yet, for a brief moment, those configurations are extraordinary. They think, love, create, and reflect. We are the universe contemplating its own impermanence. So as you rest at the end of the day, remember that the warmth leaving your body, the air cooling around you, and the fading light beyond the window are all part of the same vast current. The flow of energy through time is not something outside of you. It passes through you, connects you to the stars, and carries you forward into the future. Entropy ensures that everything changes, but it also ensures that nothing is wasted. The energy that once fueled stars now fuels thought. The heat that leaves your hand tonight may one day warm another world. In the end, the arrow of time is not cruel. It is the pulse of the cosmos itself, steady, unending, and profoundly alive. Chapter 8. Energy and Life: How the Universe Learns to Feed Itself. Life is the most intricate expression of energy the universe has yet produced. Across all scales, from the chemistry of a single cell to the metabolism of a planet, living systems are defined not by what they are made of, but by how energy flows through them. Rocks endure, but life persists only as long as energy moves. It captures, transforms, and redistributes energy with extraordinary precision, creating order within the great cosmic current of entropy. Through life, the universe has discovered a way to channel its own energy into patterns that can sense, adapt, and eventually understand themselves. From a scientific point of view, life is an open system far from equilibrium. It cannot exist in stillness. Every organism maintains its structure by constantly exchanging energy and matter with its surroundings. This steady throughput is not a luxury, but a necessity. Without a continuous supply of usable energy, the chemical reactions that sustain life would halt within moments. The second law of thermodynamics dictates that disorder must increase overall, but living systems have learned to export that disorder to their environment while maintaining internal order. They are engines of local organization operating within a universe that trends toward balance. The story begins with sunlight. Nearly all life on Earth ultimately draws energy from the fusion reactions inside the sun, where matter is converted into radiant energy that travels across space as electromagnetic waves. When this light reaches Earth, a fraction is captured by plants, algae, and certain bacteria through the process of photosynthesis. Within the chloroplasts of plant cells, photons are absorbed by pigment molecules such as chlorophyll, exciting electrons and setting off a cascade of chemical reactions. These reactions store solar energy in the bonds of sugar molecules, transforming the fleeting energy of sunlight into a stable, transportable form. The sugars created through photosynthesis become the foundation of the food chain. They fuel the metabolism of the plants themselves and provide energy to animals, fungi, and microbes that consume them. At every level, energy flows from one form to another, from sunlight to chemical bonds, from chemical bonds to movement, heat, and thought. Yet at each transfer, a portion of the energy is degraded into less useful forms, primarily as heat. The efficiency of this transfer is limited by the second law of thermodynamics, but the chain continues unbroken. Energy is never lost. It only becomes less available to perform work. Metabolism, the sum of all chemical processes in living organisms, is essentially the science of managing energy transformations. Cells rely on molecules such as adenosine triphosphate, or ATP, to store and release energy in controlled amounts. When ATP is hydrolyzed, that is, when one of its high-energy bonds is broken, the released energy powers everything from muscle contraction to the synthesis of DNA. In this way, life has evolved molecular systems that act as microscopic engines, capturing energy from one reaction and applying it to another with remarkable precision. Biochemistry, in its essence, is thermodynamics practiced at the scale of molecules. Even organisms that do not depend on sunlight have found ways to feed on energy. Deep beneath the ocean, around hydrothermal vents, life thrives on chemosynthesis, the use of chemical gradients rather than light to drive metabolism. Microbes there harness energy from the oxidation of hydrogen sulfide and other compounds spewing from the vents. These ecosystems demonstrate that life is not limited to solar energy. It can arise wherever a source of usable energy and a sink for waste exist. Wherever there is a flow of energy between contrasting conditions, between hot and cold, chemical rich and chemical poor, life can find a foothold. This universality of energy flow has profound implications for astrobiology. Planets orbiting other stars, icy moons around gas giants, and even interstellar clouds might harbor environments with sufficient energy gradients to sustain life in some form. The same principles that guide metabolism on Earth apply universally. Life requires a way to capture energy, to store it temporarily, to use it for building and maintaining structure, and to release the byproducts back to the environment. In that sense, biology is a branch of physics, the study of how energy organizes itself into living form. At higher levels of complexity, the flow of energy gives rise to ecological networks. In every ecosystem, energy moves from producers, which capture it, to consumers, which use it, and finally to decomposers, which recycle it back into the environment. The energy that enters as sunlight or chemical potential leaves as heat radiated into space. This continuous turnover links every organism into a global web of transformation. Even the atmosphere and oceans act as conduits, distributing energy from the equator to the poles, maintaining the dynamic balance that makes life possible. The Earth itself functions as a thermodynamic system, using the constant influx of solar energy to sustain a planet-wide circulation of matter and heat. Evolution, too, can be seen as an expression of energy flow. Organisms that harness energy more efficiently or adapt to new sources of energy are more likely to survive and reproduce. Over time, this drives the diversification of life and the emergence of increasingly complex systems. Complexity, however, does not contradict the second law. Each step toward greater organization increases entropy in the surrounding environment. The energy that builds a forest or a brain ultimately radiates away into space as infrared light, maintaining the overall balance of the universe. Life, then, is not a violation of thermodynamics, but one of its most elegant outcomes, a way for the universe to accelerate the dissipation of energy by creating intricate, temporary structures through which energy can flow more effectively. At the cellular level, this flow depends on membranes, thin barriers that separate inside from outside while allowing selective exchange. Across these membranes, cells maintain gradients of ions and molecules, which store potential energy. The controlled release of that energy drives vital processes like respiration and photosynthesis. In a sense, every living cell is a microcosm of the universe, maintaining order by balancing continuous inflow and outflow. It is a living proof that energy, when properly channeled, can sustain patterns of astonishing complexity. Even consciousness at its most basic level is tied to energy. The human brain, though it makes up only a small fraction of body mass, consumes a significant portion of the body's metabolic energy. Neurons communicate through electrochemical signals that rely on gradients of charged particles across cell membranes. These electrical patterns are forms of organized energy flow, transient, ever-changing, yet capable of producing thought, memory, and imagination. In that sense, awareness itself may be viewed as energy temporarily arranged into reflection. When you think, the universe's energy considers itself through you. In evolutionary history, life's relationship with energy has reshaped the planet. The rise of photosynthetic organisms billions of years ago transformed Earth's atmosphere, filling it with oxygen and enabling the evolution of complex multicellular life. Later, the burning of fossilized sunlight, coal, oil, and gas allowed humanity to amplify its reach, tapping into vast stores of ancient energy. This new power transformed civilization, but it also disrupted the balance of Earth's systems. In just a few centuries, human activity has altered the planet's climate, demonstrating that even intelligent life is bound by the same energetic constraints that govern all matter. The energy that sustains us can also overwhelm us if not balanced within the larger system. From a broader perspective, life can be seen as the universe's way of knowing itself. Through living systems, energy has learned to reflect upon its own movement. The atoms forged in stars have assembled into molecules that think, dream, and create. Every act of perception, every heartbeat, every moment of curiosity is part of the same continuum that began with the birth of the cosmos. The universe feeds itself by turning energy into awareness, by transforming radiation into the capacity to wonder where it came from. There is, in this idea, both humility and awe. Life is fragile and transient, a pattern that persists only as long as energy flows. When the flow stops, structure dissolves, and the materials of life return to the larger circulation. Yet nothing is truly lost. The energy that sustains you today will one day move through air and soil, through sunlight and stars, continuing its endless transformation. The same energy that fuels a heartbeat today once glowed in ancient suns and will someday shine again elsewhere. When we consider the future, we find that even as the universe cools and entropy increases, life's existence marks a special chapter in the cosmic story. It is the phase where the universe learned to channel energy into learning, adaptation, and consciousness. For a brief epoch before the stars fade, the cosmos is alive with awareness. Islands of energy reflecting on their own impermanence. In this way, life is not separate from the universe's thermodynamic flow, but its most expressive moment. So as you pause to breathe, think of the energy moving through you, the sunlight captured in plants, the chemical bonds broken in your cells, the warmth radiating from your skin into the air. You are part of the same current that powers oceans and stars. You are energy in motion, momentarily self-aware, participating in the universe's great experiment of feeding itself. When your form eventually dissolves, the energy will remain, taking new paths through the endless cycles of creation. Life is the universe learning how to transform, how to sustain, how to know, and in you, it continues that quiet, miraculous work. Chapter 9. The Cosmic Energy Cycle, from the Big Bang to Heat Death. The story of energy is, in many ways, the story of the universe itself. From the first instant of creation to the distant future when the stars will fade, energy drives every transformation, every structure, every heartbeat of cosmic history. Though the total amount of energy in the universe remains constant, as dictated by the first law of thermodynamics, its form, distribution, and usefulness change with time. The cosmic energy cycle is a grand narrative of transformation. From the blinding birth of the universe to the quiet equilibrium of its final age. It is a tale of creation, expansion, and eventual stillness, a rhythm that defines the past, present, and destiny of everything that exists. At the beginning, there was no space, no matter, and no time, only an infinitely dense state of energy. Roughly 13.5 billion years ago, that energy erupted outward in the event we now call the Big Bang. Contrary to its name, the Big Bang was not an explosion in space, but the rapid expansion of space itself. In its earliest moments, the universe was a searing plasma of pure energy, a uniform ocean of radiation where temperatures were so high that matter could not yet exist. Energy and matter were interchangeable, constantly transforming into one another through processes predicted by Einstein's theory of relativity. As the universe expanded, it cooled, and energy condensed into the first subatomic particles, protons, neutrons, and electrons, giving form to the primordial building blocks of matter. A few minutes after the beginning, nuclear fusion occurred throughout the young cosmos, forming the first light elements, hydrogen, helium, and traces of lithium. The universe then entered a long period of darkness as matter and radiation decoupled and light began to travel freely through space. This relic light, stretched by billions of years of cosmic expansion, remains visible today as the cosmic microwave background, a faint glow that fills all of space. It is the oldest light in existence, a whisper from an era when energy first took visible form. Over the next hundreds of millions of years, gravity began to shape the cosmic landscape. The energy of the early universe was not perfectly uniform. Tiny fluctuations in density allowed matter to clump together. As regions of slightly higher density attracted more mass, potential energy was converted into kinetic and thermal energy, forming the first stars and galaxies. Within these stellar furnaces, nuclear fusion ignited again. The same process that had briefly lit the universe in its infancy, now rekindled within the hearts of stars. The energy locked in atomic nuclei was released as light, heat, and radiation, spreading through the cosmos. Stars became the engines of transformation, turning simple elements into heavier ones, and returning that enriched matter to space through supernova explosions. Every star that has ever shone, including our sun, is part of this ongoing cosmic energy cycle. Hydrogen becomes helium, helium becomes carbon and oxygen. Massive stars forge elements all the way up to iron. When they die, they scatter these elements across the galaxy, seeding new generations of stars and planets. The energy released in these processes warms interstellar dust, powers galactic winds, and drives the chemistry of life. Even now, the light you see when you look up at the night sky is energy that has traveled for countless years, radiation born in the cores of distant suns, crossing the vacuum to touch your eyes. The universe, through its stars, has found countless ways to convert matter back into light. In the grand scale of cosmic evolution, gravity and thermodynamics play opposing roles. Gravity gathers matter, creating order and concentrating energy, while entropy drives that energy toward dispersion. Galaxies, stars, and planets represent temporary victories of order against the tide of entropy, fleeting structures in a universe that steadily moves toward equilibrium. Over time, however, even these structures succumb. Stars exhaust their nuclear fuel and fade into white dwarfs, neutron stars, or black holes. The radiant energy they once emitted spreads ever thinner as space continues to expand. The balance slowly tips back toward uniformity. Black holes, those dark remnants of collapsed stars, are key participants in the cosmic energy cycle. For decades, they were thought to be the ultimate sinks of energy, swallowing matter and light with no return. Yet Stephen Hawking's work revealed that black holes are not entirely black. Quantum effects at their event horizons allow them to emit a faint radiation, now called Hawking radiation, causing them to lose mass and energy over immense timescales. Eventually, even the most massive black holes will evaporate completely, releasing their stored energy back into the universe as low-energy photons. The process is unimaginably slow, but it ensures that no energy remains forever trapped. The universe reclaims even its darkest corners. As the eons pass, stars will continue to form from collapsing gas clouds, but each new generation will be dimmer and shorter-lived than the last. The supply of available hydrogen will dwindle, and with it the birth of new stars will cease. The cosmos will enter what astrophysicists call the degenerate era, a time dominated by fading remnants, slowly radiating away their remaining heat. White dwarfs will cool into black dwarfs. Neutron stars will drift silently through the dark. Black holes will persist as the last major energy reservoirs. On timescales so vast they defy imagination, even these will fade. Eventually, all processes that generate usable energy will cease. The universe will approach thermal equilibrium, a condition where energy is perfectly uniform and no gradients remain to drive motion or structure. This is the ultimate expression of the second law of thermodynamics, the heat death of the universe. In this final state, every star will have burned out, every atom will have decayed, and all that remains will be a thin mist of radiation, evenly distributed across an ever-expanding space. The universe will not end in fire or collapse, but in quiet, a cosmic stillness where change itself comes to rest. Yet even this apparent stillness holds mystery. Some cosmological models suggest that the expansion of the universe might continue indefinitely, driven by dark energy, causing space to stretch so rapidly that galaxies disappear beyond each other's horizons. In that far future, local regions of the universe will become isolated, each one fading into its own pocket of darkness. Other models speculate that the vacuum energy of space might one day shift, triggering a new expansion or collapse, a cyclical rebirth of cosmic energy. Whether the universe fades into eternal quiet or transforms into something new, its story remains a continuum of energy, never destroyed, only changing form. What began as a blinding flash of pure energy becomes in time complexity, stars, planets, and life itself. Through biological evolution, a portion of that energy becomes self-organizing, capable of reflection and creativity. Human thought, the very act of contemplating the universe, is a consequence of energy flowing through neural networks, a continuation of the cosmic energy cycle in a new and astonishing form. The same thermodynamic principles that govern the fusion in stars also govern the firing of neurons in the human brain. From the first light to the last, the universe is a vast system of transformations, each one giving rise to the next. Even now, the energy released during the Big Bang still defines the temperature of the cosmos. The faint afterglow of the cosmic microwave background, with its nearly uniform warmth, is a reminder that everything, every atom and every photon, shares a common origin. Each star, each planet, each life form carries a piece of that primordial fire. We are not separate from the Big Bang. We are its current expression. The energy that began the universe is still here, flowing through us, radiating outward, shaping the future. The cosmic energy cycle thus teaches a profound lesson about continuity. Energy cannot be created or destroyed, only transformed. Matter and radiation, light and gravity, life and thought, all are different manifestations of the same underlying essence. The cycle that began with the birth of time itself will continue long after our species and even our galaxy are gone. In that sense, there is no true beginning and no final end, only transformation, diffusion, and renewal on scales far beyond human comprehension. And yet, within this vast process, there is meaning. The same energy that once blazed in the early universe now sustains consciousness capable of wondering where it came from. The cosmos in us has become aware of its own unfolding. We are the latest step in the grand conversion of energy into complexity, order, and thought. Brief, but remarkable. To look up at the night sky is to see energy in motion across billions of years, and to realize that it also burns within. Every photon that warms your skin, every heartbeat, every breath is part of the same continuum that began at the dawn of time. When the final stars fade and the universe grows cold, that continuity will not be lost. The energy that once danced as light and life will persist in quieter forms, scattered through an endless expanse. Perhaps one day it will gather again, condensed into a new creation, a new beginning. Even if not, its essence remains, conserved, eternal, and unbroken. The universe's last whisper will be one of balance, not absence. As you close your eyes tonight, imagine that great flow, from the fire of the Big Bang to the glow of stars, to the light that falls upon your skin. You are part of that current, a temporary configuration of cosmic energy reflecting upon itself. Nothing you are is separate from that first light, and nothing that exists will ever truly vanish. The universe feeds itself through you, and through you, it continues to remember that it is alive. Chapter 10. You are energy, briefly organized. In the end, all complexity returns to a single simple truth. You are energy, briefly organized. Every cell, every heartbeat, every thought is the transient expression of forces that have existed since the dawn of the universe. What we call life is not a separate entity from the physical world, but an exquisite configuration of energy and matter, structured, self-sustaining, and aware. From the quantum fields that ripple beneath reality to the chemical reactions in your bloodstream, the same laws apply. The energy that animates you is not yours alone. It is borrowed from the cosmos, circulated through an unbroken chain of transformations that began with the birth of time. The atoms that make up your body were forged in the cores of ancient stars, in furnaces so hot that hydrogen fused into helium and heavier elements. When those stars exhausted their fuel, they collapsed and exploded, scattering their enriched material through interstellar space. Over billions of years, gravity gathered that stardust into new systems, forming planets, oceans, and eventually life. You are built from those same elements: carbon, oxygen, nitrogen, iron, each of which carries a story written in thermonuclear fire. In the deepest sense, you are a continuation of that cosmic process, the universe arranging its energy into the pattern we call you. From a biological perspective, your body is a dynamic energy system, never still, never static. The food you eat is sunlight in another form, chemical energy stored in molecular bonds by plants through photosynthesis. When you breathe, oxygen allows that energy to be released and converted into motion, warmth, and thought. Every second, countless biochemical reactions within your cells transform energy from one state to another, maintaining the fragile balance that defines life. You are, in effect, a controlled flow of energy wrapped in self-repairing structure. The sensation of being alive is the awareness of that flow, the continuous conversation between order and entropy. The human body is a marvel of thermodynamic balance. You consume concentrated, low-entropy energy in the form of nutrients and release high-entropy waste as heat, carbon dioxide, and water. This is how you maintain the improbable order of life within a universe that tends toward disorder. The energy that enters you does not stop. It passes through, fueling a temporary island of organization before returning to the wider cosmos. Even your thoughts, the electrical impulses traveling through neural networks, are energy in motion, fleeting patterns that emerge and dissolve in milliseconds. What you experience as selfhood is the brief choreography of this flow. On a physical level, your existence is indistinguishable from the processes that sustain stars and galaxies. The chemical reactions in your cells obey the same conservation laws that govern nuclear fusion and cosmic expansion. Energy cannot be created or destroyed, only transformed, and you are one such transformation. When you burn calories, when you move or speak, you convert chemical potential energy into kinetic and thermal energy. When you rest, your body radiates heat into the air, part of the same continuum that connects the warmth of your skin to the infrared glow of distant planets. The boundary between your body and the universe is porous. Energy moves freely across it in a continuous exchange. The human brain, too, is an engine of energy transformation. Though it represents only a small portion of your mass, it consumes a large share of your body's energy. Each neuron functions like a microscopic capacitor, maintaining voltage differences across its membrane and releasing them in controlled bursts. This electrochemical activity underlies consciousness, the sense of perception, memory, and thought. The flickering of awareness is thus a pattern of energy within matter, structured by evolution but ultimately governed by physics. The mind is not an immaterial essence, but the universe's energy temporarily arranged into introspection. In you, energy has learned to ask where it came from. From a thermodynamic viewpoint, life is improbable but not miraculous. The laws of physics permit localized decreases in entropy as long as the total entropy of the system increases. In other words, order can emerge if it helps energy flow more efficiently toward equilibrium. Life does exactly this. It accelerates the dissipation of energy by forming structures that capture and release it more effectively. The evolution of complexity, from simple molecules to cells to organisms to societies, is one long experiment in energy management. Every adaptation, every thought, every act of creation is a new way for the universe to move energy through itself. When you look beyond the biological scale, the continuity becomes even clearer. The energy that animates you once coursed through ancient forests, warmed extinct oceans, and powered long-vanished stars. Long after you are gone, it will persist, diffused, transformed, and reused. The photons emitted by your body's warmth will travel outward forever, joining the cosmic background radiation that fills all of space. The atoms of your body will one day rejoin the earth, to be lifted again into air, water, or perhaps the living tissues of other beings. Nothing in you is wasted, it only changes form. Death, seen through this lens, is not an ending but a redistribution. Even your emotions, those invisible tides of experience, are tied to energy flow. The rush of adrenaline, the calm of deep breathing, the spark of inspiration, each corresponds to shifts in the chemical and electrical states of your body. To feel joy, grief, or awe is to experience energy taking shape within the complex architecture of the nervous system. These sensations remind us that the most abstract aspects of consciousness are rooted in the same physical processes that light the stars. Emotion, thought, and identity are all ephemeral configurations of energy, patterns sustained for a brief time before dispersing back into the larger whole. From the standpoint of physics, individuality is an illusion of perspective. The molecules that make up your body are in constant exchange with the environment. You inhale oxygen that was once part of another creature, drink water that has cycled through countless forms, and eat food built from atoms older than Earth itself. You are a process, not a possession. You are not a thing that has energy. You are energy, temporarily arranged into awareness. This perspective reshapes how we think about purpose. If life is a pattern sustained by energy flow, then meaning arises not from permanence but from participation. To live is to take part in the grand exchange of the cosmos, to receive energy, transform it, and pass it on. Every act of kindness, every moment of creation, every breath contributes to that circulation. Even the smallest life form, by existing, helps the universe redistribute its energy, turning entropy into experience. In that sense, existence itself is an act of balance between giving and receiving, between order and dissolution. From a cosmological viewpoint, your life is part of a much larger cycle that began with the Big Bang and will continue long after the last stars fade. The same energy that powered the birth of galaxies now fuels metabolism in your cells. The photons that travel across space eventually become the warmth in your hands. The conservation of energy ensures that nothing is ever truly lost. Not a star's light, not a heartbeat, not a thought. The universe is a closed conversation with itself, and you are a sentence within it. Meaningful, because of what came before and what will come after. When you reflect on this, a kind of quiet understanding emerges. You are not created from the universe. You are the universe, a self-organizing ripple in its continuous energy field. The illusion of separateness arises only because energy, for a brief time, folds into the shape of self. When that shape dissolves, the energy remains, joining the same ocean from which it came. Even consciousness, as mysterious as it feels, may be nothing more and nothing less than the universe observing its own motion, energy becoming aware of its pattern. To see yourself this way is not to diminish life, but to deepen it. You are the result of billions of years of cosmic transformation, of energy learning to organize, replicate, and think. You are the descendant of starlight, the child of thermodynamics, the continuation of a story that began before atoms existed. Everything you are, everything you do, is part of that unfolding. You burn bright for a moment, as every star, every flame, and every consciousness must, before returning to stillness. But in that moment, you carry the full heritage of the cosmos. So when you feel small beneath the vastness of the night sky, remember that you are made of the same energy that fills it. The photons that left distant galaxies eons ago now strike your eyes and become thought. The energy that once shaped the early universe now moves through your hands, your heart, your voice. You are energy, briefly organized, reflecting on its own impermanence. And though your form will fade, the energy will not. It will continue its infinite journey, transformed but unbroken, forever part of the same universal rhythm. As you let that awareness settle, you may feel a kind of peace, not the peace of stillness, but of belonging. You are not apart from the universe's flow. You are its expression. The warmth you feel is ancient light reborn. Your breath is the echo of creation. You are a momentary harmony in an endless song of transformation. And when your note fades, it will not be silence that follows, but the continuation of the melody. Energy rearranging, time unfolding, the universe forever learning how to be. You made it, friend. All the way through. The universe keeps moving, but for now, you can rest. If you're still awake, there's another journey waiting, another story of stars and silence. And if your eyes are already closing, sweet dreams among the stars.